is Q-learning? Q-learning is off policy. This means that you are not playing with the same, you are not updating the same policy that you are playing with, okay? So you play with one policy, you sample from the environment, right? And as you keep on sampling your environment, you're going to have another target policy, right? You can guess that target policy is the optimal policy you want, right? And you try to estimate the value of that policy instead of using your samples to estimate the value of the policy you are playing with, right? Now, in Q-learning, what we use efficient version or a pair of these two policies. The policy that you are playing with is epsilon greedy. The policy that you try to estimate is greedy itself, the optimal policy that you want, right? So in Q-learning, what you do, you essentially do off policy with TD control, but you play with epsilon greedy, like every time you just with some probability go random, or you do greedy based on the value function that you have. But when you want to update, you think only about the optimal policy, which is the greedy approach. Okay? So let's look at how it looks like. It's going to get like super simplified as compared to the complete importance sampling case. But we needed this importance sampling because later it's going to play a lot of role in the policy gradient approaches. Okay? So, well, in Q-learning, your pi, the regional policy that you're playing with, is epsilon greedy, right? And the target one, pi bar, is greedy. It has no epsilon, right? This is the only difference. And how does it look like? Well, let's say that I am doing one TD approach. So here what I have, if I play with pi bar, which is the greedy, I'm going to update it like this, right? So this G is the sample coming from that one. So G is the return that I get and the value based on the policy pi bar, which is the greedy one, right? And now if I want to just do importance sampling, I basically need to replace this G because I am playing with pi, right? I'm playing with epsilon greedy. I need to just replace that G inside the expression with this one that we saw in the previous slide, right? Cool? But now, this pi bar to pi is going to look a bit simple. Any idea how does it look like? What is pi bar if you think about the greedy approach? When you are in one particular state, you want to play greedy. What do? You're going to find, yes, go ahead.
Arguments of the value.
Right. So this guy, this pi bar, how does it look like, the probability? It's going to be 1 at the best action. It's going to be 0 everywhere else, right? This means that this guy here that you see, right, is either 1 divided by the other one, right, or 0, right? Everybody's clear? So what you're going to do, you're going to say that this guy, right, this pi bar divided by pi, is either something, for one action, this is something non-zero. It's going to be 0 everywhere else, right? Because my greedy approach just does the optimal action, right? So this guy, you can eventually not care too much about this, but this one, which is the value in the next state, this one, you can actually simply compute it out of the Q function that you already have. How you can do it? Let's look at this together. So as I said, this guy is going to be just 1 at some point. It's going to be 0 everywhere else. But the value of the next state that you want to compute, what you're going to say? You're going to say, OK, this pi bar, whatever that is 1 in the optimal action, right? And it's going to be 0 anywhere else, right? And the value of the next state is always looking like this one, right? Everybody sees what I'm doing? So when you are thinking, you are playing with the epsilon greedy algorithm, right? Epsilon greedy update. But at every single time you would say, oh, if I wanted to play greedy, I wouldn't do random jump, right? I'm going to do the optimal action, right? Correct? So the value that you need to update with is the optimal value, which is the maximum of your Q function. You don't really need to look at that average anymore, right? So in this particular case of Q-learning, I mean, without importance sampling, it doesn't make sense, but the importance sampling going to reduce to simply computing the maximum of Q, right? So it's not that serious importance sampling argument, but the reason that it's working is because simply you are thinking of policy, right? So you would say every single state that you are in, you would say, okay, I'm in this particular state. I am playing epsilon greedy. It means that in this state, I would just either go for the best action or I randomly do an action, right? But no matter what I do, if I wanted to play greedy, then I would do the optimal action, right? Correct? And the optimal action, the value for that optimal action is eventually the maximum value I'm going to get out of this Q function that I have, right? Everybody's clear? Questions? This is why in Q-learning you're somehow working with the optimal pair. Like your policies that you're putting next to each other, they are actually behaving very well together, right? Because for greedy, you are using the same value function as you use for epsilon greedy, right? The only difference is that in the epsilon greedy, you just jump randomly with chance epsilon. In the greedy, you don't do that, right? Since you have this, you don't get into those troubles of having high variance, bad estimates. This is not going to happen. But later, as I said, you're going to see that this is happening in policy gradients, for example. Okay? So, moral of the story, longest story short, the only thing that you're going to do, instead of having that, importance sampling argument, you can just remove everything and put the maximum of the Q function. Okay? And this is, again, off-policy update. This means that every time I am playing, I am randomly maybe jumping somewhere, right? But at the same time, keep in mind that, well, if I would have had played with the optimal policy, this would have been the value, right? And then I put that value here instead of the epsilon greedy that I'm doing, right? Again, get into a new state. Maybe I am in this state because I just jumped randomly, right? Because I'm exploring, but I don't care. I would say I am in this state. If I want to play optimally, I would go for the maximum value, right? And then I'm going to update based on that assumption, right? Now, the thing that you are updating here is not anymore the Q function of your epsilon greedy algorithm, right? Epsilon greedy policy. The one that you are updating here is actually the Q function of the optimal policy, right? So you basically play epsilon greedy. Once upon a time, you randomly jump. But each time you would say, OK, what about the optimal policy? And that optimal policy is going to get updated in this form. I mean, again, this is an estimate. Definitely, it's not the exact Q function of the optimal policy. But this is the way that you can estimate that one efficiently. Questions? Yes?
How does that improve Q pi? Like, let's say Q pi goes in circles.
No, Q pi, I mean, pi, how do you build it? You build it based on this Q function, right? This is epsilon greedy. This is the point that I tried to make. When you do epsilon greedy, what do? You would say, OK, I'm going to play greedy with equal to 1 minus epsilon, right? So I'm going to use the same Q function, right? I use this Q function. If I want to be greedy, I always do the best action. When I do epsilon greedy, sometimes I just do randomly, right? But when I do randomly, I don't care about the fact that I have done randomly something, right? I do a new action. Maybe that action is random. I don't care. If I am in this state and I wanted to play with the optimal greedy approach, then my value would be this, right? And then I'm going to update the value of the optimal policy with that mindset, right? As I keep going, every single stage, somehow I would say, OK, in this state, what would be the best approach or best action based on the estimate that I have right now? Well, this is going to be the one which is maximizing the Q function, right? So maybe I'm not doing it, but I don't care. The value is going to of the optimal policy is getting updated with that action, right? And I just randomly maybe jump to another one, right? When I randomly again jump to another one, I would say, okay, here, what would be the best action I could do based on any action, based on the value function that I have right now? It's going up, right? And then I'm going to say that, okay, I'm going to go ahead and update the value of going up, right? Based on what I have, right? But maybe I don't go up. I just go left, right? And I keep on going like that. Yes.
With Q-learning, we don't need to reduce the epsilon.
No, we don't
right?
know.
Because
Yes.
we're just purely using the pi as exploration.
Exactly.
We don't need to convert
Exactly.
like
This is this is the key factor that makes it work better than SARSA for low dimensional problems. Yeah, but this is a very good observation. I'm going to talk about that. Yes.
Sorry, I'm a little confused with your notations. You're saying optimal policy, but
Yes. But pi bar is the greedy one, right?
so that's approaching optimal.
Approaching the optimal, right? Sorry if I did not make it clear. But pi bar, I think in this one I make it Q star, right? This is the estimate of your optimal one. But pi bar, I told you here that pi bar is greedy, right? And if you assume that you have a good estimate of the Q function, then this eventually should be the optimal one, right? Right? Because I keep updating pi, right? And then it supposedly is going to get to the optimal policy, right? So it's somehow you have this mindset that every time you would say, okay, I am now exploring plus playing optimal, right? And now if I assume that, then how can I update the Q function of the optimal policy, right? And then I update. And then gradually I'm going to converge to that policy, right? Make sense? Okay. Questions? Yes.
Why is the importance sampling factor equal to 1?
The importance sampling, I know what you want to say. You want to say this guy is 1, this is not 1, then going to be something else, right? But the key factor is that this whole thing that you want here, okay, this whole thing that you want to update, you actually don't need to do it anymore because you can directly estimate this guy, right? So that one is not 1, so I guess this is a typo from last year I forgot to correct, but this should not be 1. This is 1 over something, pi, right? That epsilon thing, right? But then that guy is going to get multiplied with your next action because your next action is again going to be either random or the optimal action, right? They are going to cancel out, but you don't really need to do that because if you think that you are playing this S bar, is your next state when you play optimally or you play greedy, right? That one is going to be the Q value of the optimal or the maximum Q value, right? So you can just think about this whole thing and replace all of this fraction multiplied with your value of the other policy, right? Or value sampled by the other policy. You can just replace all of it with that maximum, right? But you're right. I mean, this is again a typo. This is 1 over pi of that thing, which I forgot that one, right? Questions? No question? Okay, so if you have no question, then let me just wrap up the Q-learning algorithm. So this is the Q-learning algorithm, what you have here. So you're going to start with a bunch of episodes. Now we get into one episode. You initially sample one random state, and then you go inside the trajectory, right? Each time you are going to update your policy to be epsilon greedy, it means that at any state, you could either go for the best action based on the estimate that you have right now, or you can just randomly jump to one action, right? So you can do that. Then now that you take your action, then you're going to get the next state, right? Once you are in the next state, you are going to just update your optimal Q function, right? So you would say that my optimal Q function in this particular state in action is my sample minus whatever I had. I just add up this increment to whatever the estimate was, right? And what is this particular sample? Well, this particular sample, you look at the state that you have, I mean the next state that you see, and you don't care about the action anymore, right? You don't really need to know what is AT plus 1 because you already know what that would be if you want to play optimal, right? If you want to play optimal, in the next state, the thing that you do is you just take the best action, right? And this is going to give you the best Q, the maximum Q, right? So that is the only difference. So instead of having in this G, gamma, this gamma times Q of your policy, next state, next action, you just replace it with a maximum Q value, right? And this maximum Q value is supposedly the value you would get if you would have had played greedy, right?